Okay, well, welcome everyone. Our speaker today is Martin Balko from Charles University in Prague. He was also before that a postdoc at Ben Gurion, I believe, and the Renyi Institute of Mathematics. His work is on all sorts of flavors of combinatorics, and today he will speak about new results in combinatorial geometry. So whenever you want to start.
Okay, thank you, Pablo, for a nice introduction. So, hello, everybody. I will be talking about the joint work that we had with a group of Hungarians. It's Gergely Ambros, Nora Frankl, Attila Jung, and Martin Ásody. And it will be about Helly numbers of exponential lattices. Now, since the name Helly popped out in the title, let me state the famous Helly's theorem. So Helly's theorem states that for every positive integer d and every collection f of convex sets in d-dimensional Euclidean space, if any d+1 or fewer sets from f have a non-empty intersection, then the whole collection has a non-empty common intersection. So there will be a point Rd that is the sets from f. So let me illustrate this statement on a picture. So here on the picture, we have a collection of 4 convex sets, and as you can see, it's in the plane, so d is equal to 2, and then we require every triple to have a common intersection. And as you can see here, every triple of the sets from our family has a non-empty intersection. The intersections are denoted by these orange areas, and because we have these intersections that are non-empty, and because we have convexity, it is guaranteed by Helly's theorem that there is a point in common to all of the sets in our convex family. So as you can see, this common intersection of all the 4 sets is non-empty. Now, this is a classical result in discrete geometry. It's, as the name suggests, it was discovered by Helly, and it's almost more than 1 century old. The assumptions in the theorem, the fact that we have convexity and then we are looking at intersection of d+1 tuples, both of them are necessary because, for example, if you in the plane, if we only require pairwise intersections to be non-empty, so then we can have some sets like this. Here we have 3 sets that have non-empty pairwise intersections, but as you can see here on the right, these sets do not have non-empty common intersection. So the common intersection is empty, so we need to have at least d+1 tuples to have these intersections. Also, if we give up convexity, then the statement also doesn't hold. Here we have 4 sets that not all of them are convex. We still have intersections that are non-empty intersections of triples of these sets. So as you can see here, we have a common intersection, here as well, here also. Here there is a tiny one, but it is still non-empty. But as you can see on the right, the common intersection is empty. So if we give up convexity, we also cannot obtain the conclusion of Helly's theorem. So the assumptions are necessary. Now there are many variants and generalizations of these results, and I will focus in this talk to a particular one, which is sometimes called restricted Helly numbers. So we will study the variant of Helly's theorem, which is somehow related, or which is the variant is about coordinate restrictions. So let me state this definition of Helly's number. So we will have some positive integer d, and we will have some points at S in the D space. And then the Helly number of S, so Helly number of this point set, which will be denoted by HS, is the smallest positive integer n, if it exists, such that the following statement is true for every finite family of convex sets in the D space. If the intersection of n or fewer members of F contains at least 1 point of S, then F contains at least 1 point of S. So then the intersection of all convex sets from F contains at least 1 point of S. So this is analogous to the statement that we had in Helly's theorem, but here we require intersections to contain point from our point set S. So we are not happy with some arbitrary intersection. We really want to have points from our point set S inside the intersection. So let me again show you some picture which somehow, I hope, illustrates this statement. So here we have some finite family of convex sets. As you can see, the triples contain intersection, have non-empty intersections, and they contain always points from our fixed point set, which is denoted by these orange and black dots. And then if we have this condition, then there is a point of our point set S that is in the common intersection of all convex sets. So it's very similar to Helly's theorem, and the main difference is that we require this intersection to contain points from our point set S. To digest the definition, observe that if our point set, if no such number n exists, then I will write that this Helly number of S is infinite. So I will just write Hs is equal to infinity. Now to digest the definition, observe that if our point set S is the whole space, is R to D, then we obtain Helly's theorem, and this gives us that, or by Helly's theorem, we have that the Helly number of this space is equal to D plus 1. Let me show you one more example. This is so-called Doignon's theorem. So he studied the case where our fixed point set S is the d-dimensional integer lattice. And he determined Helly's numbers of these integer lattices or grids. This is well-known Doignon's theorem from the 70s, where he proved that the Helly number of the integer lattice is exactly equal to 2 to the d. So it's much larger than in Helly's theorem, where we have d plus 1. Here we have 2 to the d. And it's exact. So this is tight. It can be witnessed by the following example. So take a point set Q, take set Q, which is a set of 0, 1 vectors of length d. And now, as our family of convex sets, consider the convex halves of point sets that are obtained from Q by removing one fixed point x. So this gives us 2 to the d sets, convex sets, and they have the property that intersection of any 2 to the d minus 1 sets from this family contains a lattice point, but intersection of all of them, of all of the 2 to the d sets, does not. This is because if we have 2 to the d minus sets, then there is one element x that is in all of them that was not removed, and this lies in the intersection. But if we look at all the 2 to the d sets, then each one of them has some element x removed, and therefore none of the lattice points can be inside the intersection, because each of the points from the 0, 1 to the d was removed in one of the sets, and therefore the intersection doesn't contain an element of the lattice. Here there is a picture of it. So here we are in the plane. We have 4 convex sets. So those are the triangles, this one, this one, this one, and this one. Sorry, let me do it again. So this, we have this triangle, then we have this triangle, this triangle. If you look only at 3 of them, then in the intersection there is always a lattice point. It will be one of the corners. But if we look at the intersection of all the 4 sets, then the intersection doesn't contain any lattice point. So there will be this point in the middle, for example, but this is not a lattice point. So from the point of view of the lattice, the intersection is empty. And this example shows that the Helly number of this d-dimensional lattice is at least 2 to the d. And it can be shown that this is also at most 2 to the d. So this is variant, or those are Helly numbers of some particle sets in lattices. Let me reformulate this definition so that it's easier to think about, because I typically have problems thinking about this Helly statement, because you have to keep in mind some families of convex sets and some intersections and so on. But luckily there is a very nice reformulation proved by Hoffman and independently by Doignon, which puts this definition of Helly numbers into different perspective using so-called empty polygons. So an empty polygon in my point set S is a convex polygon, which is vertex set P, such that if I take the convex hull of P and I intersect it with my point set S, then the only points of S that I meet in this convex hull are exactly the vertices, the points from P. And then the size of this empty polygon will be just the number of vertices of this polygon. So this is the size of P. So let me show you some example. So let S be again integer lattice. So there is a portion of integer lattice. Now this is an example of empty polygon in S. So this is a polygon of size 4 because we have 4 vertices. And as you can see, if I take the convex hull of these 4 vertices, then the only points of the lattice that are contained there are exactly these 4 vertices. So this is an empty foregone in this lattice. This example, this red one, this is convex 5-gon, but this is not empty in S because, as you can see, if I take the convex hull of its vertices, then there are some points of S that lie in this convex hull. The same problem would be if some of the points lies on the boundary that we also do not want. If it lies on the boundary and it's not a vertex. And now, amazingly, this maybe rather difficult definition of Helly number of S can be somehow simplified, because Hoffman and Doignon in the 70s showed that if my point set S is discrete, then the Helly number of S is equal to the maximum size of an empty polygon in S. So whenever we will be talking about these Helly numbers, you can keep a simpler image in your head. It will be just the maximum size of an empty polygon in S. So from now on, whenever I will talk about Helly numbers, I will essentially talk about the maximum size of empty polygons in my sets S, which is a good news for me because I'm typically used to work with these holes or empty polygons, but I'm not so much used to work with Helly's theorem or Helly statements. But in this case, it seems to be the same. Now, the theory of restricted Helly numbers is somehow popular. It's developing rather quickly. There are various results, and the sets that I will be mostly focused on are so-called product sets. And a product set is just a Cartesian product of some discrete sets A1 up to AD. So the whole set is discrete, and these sets A1 and AD, we can think of them as sets that determine coordinates in one of the D directions. So in particular, for example, lattice, integer lattice is a product set because I can take each AI to be just a set of, say, positive or non-negative integers, and then I will obtain this non-negative portion of integer lattice. Now, Dillon quite recently studied restricted Helly numbers of various product sets, and he developed a method which shows that the Helly numbers of various product sets are infinite. So his method, for example, yields the following result. He showed that if we have a product set, where the coordinates are determined by some polynomial of degree at least 2, then the Helly number of such product sets are infinite. So he found arbitrarily large empty polygons in such product sets. Now, if P, if the polynomial is degree 1, then we obtain somehow a fine image of integer lattice, and then by Doignon's theorem, these numbers are finite. But if the coordinates grow faster, if they are determined by these integer values of these polynomials, or integer values, images of integer values via some polynomial of higher degree than 1, then suddenly we obtain large holes, and the Helly number is infinite. So this is quite nice result. However, this Dillon's method, it doesn't give us everything. There are point sets or product sets for which it doesn't say anything. So for example, if we have product set in the plane where the coordinates are powers of 2, then Dillon's method doesn't give us anything. We don't know if it's finite or not. So based on this example, Dillon posed the following open problem. We call it problem 1. He asked, what is the Helly number of this particular set? So this product set where the coordinates are powers of 2. Now, when I saw this problem for the first time, it was this year at the workshop in Hungary, I immediately thought, okay, this has to be the Helly number of this set, it has to be infinite. Because it seems on this example with polynomials that the sparser the set is, the easier it is to obtain large holes, and more likely it will be infinite. And these exponential coordinates somehow suggest that it's very sparse, and therefore that this number will be infinite. And at the workshop, we looked at this problem and we studied it, and eventually we were able to solve it. And actually, our results are somehow more general. So it's not only about this product set with coordinates being powers of 2. It's more general. So we study so-called exponential lattices. So for some real number alpha, which will always be larger than 1, let L alpha be the exponential lattice which is a product set where the coordinates are powers of alpha. So alpha is the base. So in particular, if alpha is equal to 2, then this L2 is exactly the set Dylan asked about. And now we looked at Helly numbers of these exponential lattices. And somehow, to my surprise, we were able to provide finite bounds on the Helly numbers of these sets for any alpha. So it turns out that these numbers are actually finite. They are not infinite. So this is my or our first result. Let's call it Theorem 1. It says that no matter what the base is, no matter what alpha is, as long as it is larger than 1, we know the following. So the Helly numbers of these exponential lattices are at most 5 if alpha is at least 2. And for any other alpha, we have this following upper bound. So it's 3 times roughly logarithm of alpha divided by alpha minus 1. So for any alpha larger than 1, this is a finite number. Now, some observation about the statement. So observe that the upper bounds are decreasing as alpha is bigger and bigger, so with increasing alpha. And the minimum is attained for alpha equal to 2. So the minimum upper bound that we get here is this 5, which is for alpha at least 2. And now there are certain breaking points where these upper bounds are getting bigger and bigger. The breaking points are determined by certain polynomial equations. And this essentially says that the smaller alpha is, the larger holes we have there, or the larger our upper bound is. So those are the upper bounds. We also have lower bounds, and our lower bounds are tight for any base, which is at least the golden ratio. So the golden ratio will pop out somehow often in our results, which is also a little bit surprising. So our lower bounds are as follows. So this is Theorem 2. It says that the Helly number of my exponential lattice L alpha is at least 5 if alpha is at least 2. It's at least 7 if alpha is at least the golden ratio and less than 2. And for every other alpha, we have at least the following lower bound. So it's at least roughly square root of 1 over alpha minus 1. So you can see that what I said is really true. As alpha gets smaller, the holes that we get, or the empty polygons, are getting bigger and bigger. So then the Helly numbers also grows and grows by this result of Hoffman. So our bounds are tight for alpha equal to 2. So this gives a solution of problem 1. Actually, our bounds are tight for more of the alphas. So if alpha is at least 2, then we know that the Helly number of this exponential lattice is exactly equal to 5. If alpha is at least golden ratio and less than 2, then we also have a tight bound. We know that the Helly numbers of this alpha, L alpha, are exactly equal to 7. So you can see here the breaking point, one of them. So the breaking point is this is 2, where we jump from 2 to 7. The next breaking point is the golden ratio, where suddenly our upper bound jumps, I think, up to 9 or something. Now you can ask how close are the upper bounds and lower bounds that I showed you. So you can express alpha as 1 plus 1 over x, where x is any positive real number. And then we can study the growth rate in terms of x. So the Helly number of this lattice L alpha, where alpha is 1 plus 1 over x, grows at least as a square root of x, roughly, and at most as roughly x times logarithm of x. So you can see that our upper bounds and lower bounds, they do not meet. There is still some gap, but at least we can see that it grows to infinity as we are getting closer and closer to 1. Now, I said that some minutes ago that when I saw it for the first time, I thought the density might play a role, and the fact that it is sparse means that there will be large holes. But this is actually not true, and it turns out that the density actually doesn't matter, because we can slightly perturb points of our exponential lattice, and then we can drastically change the Helly numbers. So this follows from Binet's formula, which is a closed form formula for the Fibonacci numbers, and from the following result that we obtained. So it is a rather simple proposition, which says that the Helly numbers of product sets where the coordinates are determined by Fibonacci numbers. So these Helly numbers are infinite. And now, by Binet's formula, Fibonacci numbers actually converge to the exponential with base equal to the golden ratio. So you can think of this product set as somehow a perturbation of an exponential lattice. And for this exponential lattice with the golden ratio, we know that the Helly number is equal to 7. But for this one, it's infinite. So even slight perturbation can change the results somehow drastically. So this is one other result that we have. And finally, last result that I want to mention. So we wanted to settle these exponential lattices in the plane completely. So we also looked at these non-diagonal exponential lattices. So let L alpha beta be the exponential lattice where the rows have coordinates or columns have coordinates with base alpha, and the rows have coordinates with base beta, where alpha and beta are arbitrary real numbers. They do not have to be the same, and they are, but they all are always larger. Now, a natural question is, what are the Helly numbers of these exponential lattices? So we go even more general. Is it the case that they are always finite? Can they be infinite? Know that L alpha is equal to L alpha alpha. So if the bases are the same, then we get the diagonal lattices that we discussed so far. But this is really more general setting because the basis for rows and columns can be different. Now we fully characterize these exponential lattices that have finite Helly numbers. So we have a complete characterization. So let me put it as our theorem 3. So let alpha and beta be some real numbers, maybe different, but larger than 1. And then we prove that the Helly number of this non-diagonal exponential lattice is finite if and only if. And now you can think what will be the right condition. You can try to guess. It's again a little bit surprising, I think. So we show that this number is finite if and only if logarithm of beta with base alpha is a rational number. Or you can put it differently, logarithm of beta divided by logarithm of alpha is a rational number. So the rationality somehow plays a role. And now, if this logarithm is rational, then it's supposed to be a finite number, this Helly number. And we even have some bounds on it. So those are the bounds that we have if this logarithm is rational and this number is infinite. Actually, I don't know why there is 2. There shouldn't be this exponential. So it's just p times q, pq times this Helly number of alpha, alpha to the power of p. So this should be also hl. So to give you an example, so if I have non-diagonal lattices, say L2, 4, then this theorem tells me that the Helly number is at most 9. Because 4 is 2 squared, so you can think of it, so the logarithm is rational. But if I have exponential lattice with bases 2 and 3, then logarithm of 3 with base 2 is irrational, and therefore, by this theorem, this Helly number is actually infinite. So then we can find arbitrarily large empty convex polygons. So those are our results. Now I would like to sketch at least very, very high level overview of the proofs, like what are the main ideas. But I will not go deep, really just I will touch the surface. So let's start with theorem 1, where we prove the finite bounds on these diagonal exponential lattices. So I will focus only on the case where alpha is equal to 2. So those are this is the exponential lattice that was considered by Dylan. So we want to show that the largest empty polygon in L2 has 5 vertices. And we also want to show, we know that it is tight. So let's have a look at this exponential lattice. So this is the initial portion of such a lattice. As you can see, the coordinates grow as a power of 2. Now to show that there is an empty convex polygon of size 5, you just have to find one, and it's not that difficult. So there is, for example, this one. So it has 5 vertices, it is empty, so the Helly number is at least 5. So the lower bound here is not difficult, but we want to now show the upper bound, that this is at most 5. So if we are given some convex polygon in L2, what we do is that we partition its boundary into 4 convex chains. So if I have some polygon, convex polygon in my lattice, exponential lattice, we will partition its boundary into 4 convex chains. We call them convex chains of type 1, 2, 3, and 4. They are determined by the slopes. So here we go like this, here we go this, like this, and like this. We might have vertical edges and horizontal edges. For them, we have to somehow say of which type they are. So this horizontal edge is of type 2, this is of type 3, this is also of type 3, and this vertical one is of type 4. And now if we have partitioning into these 4 convex chains, then we estimate the size of each such chain separately. So we will use various methods for each type of the chains, and we will then sum the bounds that we obtain, and this will be the total sum on the size of this convex polygon. Now, some cases, some of the types are easier to handle, for example, because rapidly decreasing slopes and so on. So perhaps the simplest case is this type 1, because it actually turns out that if our polygon is empty, then the chain of type 1 contains only a single edge. So you cannot have 2 edges. The reason is that if you would have 2 of such edges, then the next one has to form a concave chain. But then, because the coordinates grow somehow rapidly, this edge will have the next column above it. So it cannot be there. It will not have a point, the other endpoint that we could use. Some of the other types are more difficult. So types 2 and 4 are more difficult than 1, but they are easier than 3. And they are actually symmetric. So if you deal with one of them, then you deal with both. But this type 3, this is the most difficult one. And to handle it, we used a certain auxiliary lemma that I will try to demonstrate. So this auxiliary lemma that helps us with this type 3 says that if you have a point of your exponential lattice, and if you have 2 points of your exponential lattice that are in a row above it and are consecutive, so there is no point of the exponential lattice between them, then if you take a wedge determined by these 3 points, then all the points in your exponential lattice that lie inside in the interior of this wedge, all of them lie on a single line that goes through the origin. So then your points are really limited. And this is used in the proof that you cannot have 2 long convex chains of type 3 in your empty convex polygon, but all the cases require certain case analysis and then put them together carefully so that your upper bound is as small as possible. It's also rather tedious, so I will only stick with this high level overview, and I will not go too deep into the proof. So this is the whole sketch of the proof, the main ideas. But as I said, if you want to carry it out with all the details, then it actually gets more difficult. So let's claim that this theorem 1, the sketch of the proof, is done. And let's go for theorem 3, which was about these non-diagonal exponential lattices. And let's show how the characterization goes, how to prove that we have finite Helly numbers if and only if this logarithm is rational. So let's start with the finite case. So we want to show that this Helly number is finite if this logarithm is a rational number, say some p over q. If this is the case, then we notice that we can actually partition our exponential lattice into p times q affine copies of this diagonal exponential lattice L alpha to the p. And then because this is a diagonal exponential lattice, we can apply theorem 1, which was about these diagonal lattices, and this will give us some upper bound using pigeonhole principle. So let me illustrate the idea. So we start with some non-diagonal exponential lattice, say L24. Now we can partition it into affine copies of L alpha p, which in this case is L4, because p is equal to 2 and q is equal to 1 in this case. So we have 4 copies of L4. And now if I have some convex polygon, which ideally is supposed to be empty in my non-diagonal lattice, Then by pigeonhole, there will be some large portion which contains points from single copy. So we will then stick to this portion. Here in this example, this is the red copy. And then we will apply theorem 1. By theorem 1, we know that this red copy, if it's empty, it has at most 5 points. And by pigeonhole, this provides some finite upper bound in this case. So in this case, if we want to prove a finite upper bound, it's really just a reduction to this diagonal variant that we solved before. So this implication is rather easy. It's not that difficult. The fun part is when we want to show the infinite bound if the logarithm is irrational. So let's assume that this logarithm is irrational, and we want to find arbitrarily large empty convex polygons in our exponential lattice. Now this actually falls more into number theory because what we do, the main ingredient to find these large holes, is to use theory of continued fractions. So let me just state what a continued fraction is. So if I have a real number r, then the continued fraction of r is expression of the following form. So you can see that it is a little bit recursive. So it's some a0 plus 1 over a1. And then we are doing the same thing over and again. So a1 plus 1 over a2 plus 1 over a3 and so on. Where a0 is some non-negative integer and a1, a2 are some positive integers. So these continued fractions are studied quite a lot in number theory. There is a compact notation for them. So the continued fraction of r, instead of writing this crazy expression, is just written using these brackets. So a0, a1, a2, and so on. To give you some examples, so the continued fraction of logarithm of 3 with base 2 starts with 1, 1, 1, 2, 2, 3, 1, 5, 2, and then it jumps to 23, and it continues infinitely. And for example, continued fraction of the golden ratio, it's perhaps as simple as it can be because it contains only ones, but it's again infinite. In fact, these continued fractions are infinite if our real number is irrational. So then we have infinitely many coefficients. And this is what we use to create these large holes. And we also use two lemmas, which again fall more into number theory. So let's define convergent as this fraction. So this convergent of r and convergent of r. So this is fraction of type written as Pn over Qn, which is just the initial portion of the continued fraction, which is determined by the first n plus 1 coefficients. So this defines some sequence of fractions, convergence, and these convergence are best rational approximations of this real number r. What does it mean precisely? Well, being best approximation, it means that for any fraction pq, where the denominator q is less than qn, the denominator of the n convergent, satisfies that the absolute value of rq minus p is strictly larger than r times qn minus 1 minus pn minus 1, and again in absolute value. So this somehow shows that these are the closest fractions to your real number if you have some restriction on the size of the denominator. And this is what we use in the proof. But this is not strong enough for us in certain case. In certain case, we will need a similar result, which is actually quite a new one. It was recently proved by Hanschel and Turek, guys from Czech, and it's about semi-convergence. So semi-convergence, those are expression of this form. So you have Pn plus IPn, Pn minus 1 plus IPn divided by the same expression with Q. And if you take these with an odd, so you take the odd ones and all the i's that are between 0 and an plus 1, then they show that those are best lower rational approximations of R. So the convergence as approximation, they both work somehow both ways. But these ones, the semi-convergence, they work only in one direction. So they are sort of one-sided approximation. And what does it mean? Being a best lower approximation? Well, this means that essentially this is true, but without the absolute values. So it's really one-sided. But the same expression, but without the absolute values, is true. And this is what we will use. So those are the very rough basics from continued fractions that are handy for us. Now we want to use it to construct arbitrarily large empty polygons in my exponential lattice. So as our real number for which we use the continued fractions, we will define it as this logarithm. Because this logarithm is irrational, the continued fraction has infinitely many terms. And now we will distinguish actually two cases. So first case, if this R, if our logarithm is a restricted number, which means that in its continued fraction, all the coefficients are bounded by some constant. So for example, if my logarithm is the golden ratio, then it is restricted because as we saw in the example, all coefficients are then 1. So all of them are bounded by some constant. And if we use this, then we can use lemma 1 and to show that we will obtain empty convex polygon. And the way we obtain it is that we choose these convergence to be exponents in the points from our exponential lattice, and we take only these exponents, the convergence that are smaller than r, so we lie below y equals to x line, and those will they will eventually form an empty convex polygon. I will show you a picture in a minute. So this is the first case. If r is restricted, then we use this lemma 1. We take convergence as exponents in the points of our empty convex polygon, and that's it. If R is not restricted, then this is the case where we use lemma 2. So this is where we use the semi-convergence. Because if R is not restricted, then the coefficients AI grow infinitely. They are not bounded. They can be larger than any given number. So if I'm given number m and I want to construct an empty convex polygon of size m, then I will take a coefficient AI for some sufficiently large I, so that AI is larger than m. And then I will use the same trick as before. So I will define exponents of my points as semi-convergence that are determined by this coefficient AI. So there is AI of them. So there is m of them because AI is larger than m. And this will produce eventually empty convex polygon of size n based on this lemma 2. So let me very roughly show this on the picture. So assume that so we are in the restricted case. So we have this real number r, which is restricted. Let's focus on classical integer lattice. So this is not exponential lattice. This is just a standard lattice. And let's have a look at this line y is equal to rx. Now I will take the convergence, so this Pn over Qn, and I will use them to define points here. So a convergent Pn over Qn will determine a point Pn Qn. So the Pn will be the first coordinate, and Qn, the denominator, will be the other coordinate. And if I take the first two convergence, then together with the origin, they will give me this triangle. Then I can take the third convergent. This will give me this third green point, and I have this square. Then I take the fifth one. So this is this one. And as you can see, I'm constructing some area, some green area. Then I take another convergent. This will be this one. And altogether, what I'm doing is that I'm constructing two convex chains. One is above the line. The other one is below this line. So that the area between them, the green one, is empty of points. So there is no lattice point which is inside the green area. And this is because these convergence are the best approximations, best rational approximations of R. So then I am obtaining this empty, not necessarily convex, but this empty area, which is formed by two opposite convex chains. Now, if I take these green points and I will use them as exponents in my exponential lattice, and I will take only these points that are below. So these points that are below the line, then it will also give me some convex chain in my exponential lattice. Here, the chain was actually concave. But here, if I use them as exponents, it can be shown that if my number is restricted, then it will actually be convex. So it's somehow oppositely directed. And what is nice is that the property of emptiness, it still holds. The fact that the convergence are best rational approximations is still sufficient to show that this green area is still empty. And because this is convex, we have an empty convex polygon, which can be arbitrarily large in my exponential lattice. And this eventually proves this infinite lower bound. In this non-restricted case, we do the same thing, but with convergence. But all the ideas are very similar. So that would be the sketch of this proof. Now let me conclude with some open problems. So there are several of them. We have not solved everything by far. So the first one is rather obvious one. It's about improving the estimates on the Helly numbers of these diagonal exponential lattices. As I showed you, our lower bound and upper bound, they are still not tight. There is still a gap between them. If alpha is smaller than the golden ratio, so it would be nice to close it, at least asymptotically. The second problem is about higher dimensions. So everything that we proved is only in the plane. We have never considered higher dimensions, but it's a natural problem. For example, Doignon's theorem holds for any dimension, but we stick only to the plane. But the natural question is, what happens in higher dimensions? Are these Helly numbers of exponential lattices always finite, or are there cases where they can be infinite, and so on? So if dimension is at least 3, we don't know anything. Maybe our method can be extended to this case. We really haven't tried, but I can imagine that if you would aim for some precise bounds, then it would be actually quite tedious. But maybe if you don't aim for tight bounds, but some finite bounds, then maybe it will be easy. And lastly, I would like to mention conjecture, which is not ours. It was posed by Delora et al. And it's about product sets where the coordinates are determined by prime numbers. So this p squared product set. So they believe that the Helly number of this creature should be infinite. So this is their conjecture. It might be actually the case. There is a lower bound found by computer, which shows that this is at least 13. And maybe in this case, some of the methods that we used can be somehow used. I don't know, for example, these continued fractions can be used, but somehow restricted to prime numbers. Maybe there is a result in number theory that can help with this case. This might be also interesting to look at. But that's it. Thank you very much for your attention. So if you have any questions, feel free to ask. There is something in the chat.
I do have a question.
Yes.
In the tight bounds you showed, like the lattice number for 2 to the n, and the Helly number was 5, and then it jumped to 7, and then you mentioned it jumped to 9. Is it always an odd number, or just for the cases?
I don't think it's always odd number. Maybe I remember this 9 wrong. Actually, maybe it's larger. So you can actually see it from the formula for the upper bound. But it's only those jumps are only about our upper bounds. So this is not like a true value, because I suspect that our upper bound is actually not tight, that you can improve it. Let's find the slide. So there is this logarithm. Here. So here are the jumps, and it's only jump in this formula. So if alpha increases because there is a ceiling function, then you get these sudden jumps, sort of. But as I said, these jumps are determined by some polynomial equations, because if you try to estimate the sizes of the convex chains, then you immediately get some conditions on this alpha that actually goes up. And yeah, I cannot tell much about the jumps, how large they are, but I don't think it will always be odd number.
And of the two bounds, you had the one that was like a square root of x, and the other one which was super linear in x.
Yes.
Which one do you think is closer to the truth?
My guess would be that actually neither of them. I can imagine that the truth is somewhere in between. So the lower bound is like square root of x, if I use this expression with x, and the upper bound is x log x. I can imagine maybe it's linear, which in this case it would be closer to the upper bound. Linear might be a good guess. I see places in our proof of the upper bound which perhaps can be improved, but it would be maybe difficult. And the lower bound, this is just one construction that we found that works, but we do not claim that this is the smartest one. It's actually quite simple. You just use a hyperbola and that's it. You can write it in a paragraph. Thanks for the questions. Any other question?
I have a question. So you mentioned that the Helly number for the Fibonacci lattice was infinite. Is this used a similar construction where you like take a line and look at some sort of polygon underneath this line?
Yes. So actually, you use this convergence from Bennett's formula. So you have this sort of line, and then you have the Fibonacci numbers. They sort of converge to it, and then you just take this polygon. This will be the empty one. So you just take the ones that are really approaching this line. So in the lattice, that they would be on a line, but here they are sort of on a curve, on a convex curve, or concave. It's maybe similar to the method that you used for the polynomials.
Yeah. It seems, would this then apply to things maybe more generally that like converge to something exponential in a generic way?
Yes, it might be.
Great.